Good afternoon. So today we'll continue our discussions on caches. So maybe some of the stuff that I'm going to talk about at the beginning might be just repetition from what you guys have seen in other courses, but just bear with me. We'll get into the operating system stuff soon. Okay, so I guess we're here. So we're talking about hierarchy of caches to reduce the missed time, so that if we miss in one level, instead of going all the way to memory, we can have a chance to find the data we're looking for in the next level cache. Now, in this case, the missed time at level X is equal to the average access time at level X plus 1, obviously. Now, what is average memory access at a certain level? So this is equal to the heat time at that level plus miss ratio at that level times miss time at that level. So in particular, if we are looking at the CPU as the reference point, the average access time would be the heat time at M1 plus the miss ratio at M1 times miss time at M1. Now we can substitute the miss time at M1 with the average access time at M2. And then we can just expand average time at M2, which is equal to heat time at M2 plus miss ratio at M2 times miss time at M2. And then we can just keep going, right? We can just substitute miss time at M2 with average time at M3. And now we can expand the average time at M3. So this basically gives us an equation to get the average memory access time at any reference point. In this particular one, we're looking at CPU. Okay, now when you're designing caches, there are a bunch of questions that you have to answer. First one is, so let's first set up the example, then we'll look at the examples that we might have. Let's say that you have a memory that is of 2 to 5 bytes, or maybe 2 to 5 blocks. Doesn't matter. But then let's assume that you can. In this particular example, I have a 2 to 5 bytes, right? So I have 32 bytes in my memory, which is what you can see here. Let's assume that your cache is only 8 byte. And let's assume that we can cache every single byte in this example. So the block size is 1 byte. Okay, so this is the setup. So obviously we don't have as much capacity in our cache as we have in memory, and that should make sense. The cache is smaller. Now, let's assume that the CPU wants to access a certain byte. In this example, 01100 byte. So that's the address. Now, how can I find that address in my cache? How can I know if this particular byte is cached in my memory? So that's the first question we have to answer. We have an address for a particular byte in memory. We want to see if that particular byte is in cache. The second question that we have is, let's assume that we can figure that out and know if that byte is in cache or not. And let's assume that it's not. Now I want to bring it to cache. Where should I put it? So when it comes back, where in the cache should I put this byte? And the third question we have to ask is, let's assume that the cache is full, and for me to bring a new data, I have to evict an already existing data from my cache. Which one should I evict? So let's look at these questions one by one. So let's start with the first one, where to put blocks in cache. I mean, if I go back, these two questions are very related, right? So where to look is kind of related to where did you put it last time, right? So the cache hierarchy is usually designed so that we divide our cache into disjoint sets, and we map each set to each block in our memory. So each block can go to only one set. There's a one-to-one mapping between our blocks and our sets. Now, with each set, there might be m number of blocks in that set. So we divide our cache into different sets. Now each set has a certain number of blocks in it. That would say the set associativity of our cache. So an m-way set associative cache is a cache that has m blocks per set. So if I have 4 blocks per set, that means that that my cache is 4-way set associative. Now, let's go back to this the example we saw here. Let's say I want to have a 2-way set associative cache. That means that each set is going to have 2 blocks. In this case, each block is a byte. So I'm going to have 2 bytes per set. My cache has 8 bytes, so I'm going to be having 4 sets because each set has 2 blocks. So the number of ways per set and the size of the cache tells us how many different sets we have in the cache. Now, if the number of blocks per set is equal to the size of the cache, meaning that all the blocks in the cache belong to the same set, this means that there is only one set, and that would be called a fully associative cache, a cache that has only one set and all the blocks in the cache belong to that particular set. Now, this is the most flexible design that you can have. The reason is this one that we said here. We said we need a one-to-one mapping from sets to memory blocks. If I only have one set, this means that all my memory blocks are mapped to the same set. So this gives me the utmost flexibility because I can put this block anywhere I want in cache. Now, the least or the most restrictive way is to have one-way set associative, meaning that each set has only one block. This would give you the least flexible design because now each memory block is mapped to a single cache block. So there is only one place that each memory block can go. So this is the least flexible. Compare that to this one. In the fully associative, each memory block can go to any cache block. So that's the most flexible design. Now, with this flexibility comes the performance cost. So in order to implement such a cache that allows each memory block to go anywhere in the cache, you will have a lot of circuit, and that adds a lot of latency. So a fully associative cache is a slow cache. Now, we're not paying that price here with DirectMap caches, so that gives us the shortest access time. So there is less circuitry. for every memory block, I can look at a single cache block. So the search is very easy. At the implementation of search, there's a single memory cache block that I need to look at. Therefore, the access time is very short, and the performance is wonderful. Okay, now let's look at DirectMap Cache in the example that we have. So basically, with DirectMap Cache, I'm going to say that each memory block can be mapped to a single cache, and this is a one-to-one mapping. There is a one-to-one mapping from each set. So if I have a DirectMap cache, this means that each block is a set. So this is set 0, this is set 1, this is set 2, this is set 3, all the way to set 8. Sorry, set 7. So I have 7 sets. Now each memory block is going to be mapped to a single set. So sorry if this I made a mistake. I said one-to-one. By this, I just mean that each memory block has to be mapped to a single set. You cannot map a single memory block to multiple sets. So that's from one way to another one, there is a one-to-one mapping. Okay, now how do I recognize which set each memory block belongs to? Well, I have 8 sets that would require 3 bits. So I can look at the least significant bits of my address, and I can say I can use that as the set of my my memory block. So for every address, I look at the least significant 3 bits, and that tells me which set this address, this particular byte in memory is going to go, right? So, and that would give me, for every single address, it would give me a fixed set. So if you do that, all the addresses that end with 100 will be mapped to set 3. And all the addresses that end in 000, this one, this one, this one, and this one, they're going to be mapped to set 0. Now this answers the question we had. So if I get an address and I want to see if I have cached this data or not, I have a candidate to look at, right? I can just look at the 3 last bits and say, oh, it could be here. Now, how do I know if the data I have here is the data that I'm looking for? Maybe it's sorry, not this one. How do I know? Yeah, how do I know it's this one and not this one? So how do I know? Because both of them are mapped to the same address. How do I know if I have this data or if I have this data? Because both of them are mapped to the same set. Now, in order for me to recognize that, I have to look at the rest of the bits of address, because the rest of the bits in address are different from different memory addresses. So I can tag each cache with the rest of the address, so that when I look at this, if I see a tag of 00, then I know that the cache content is for this one, because this one has a 00. If the tag is 01, then I know that I've cached this address. If the tag is 10, then I have cached this one. And if the tag is 11, then I have cached the top one. So this is where we're going to add the tag. Let me let me get rid of this. So in order for us to recognize and identify between different memory blocks that are mapped to the same cache, we need to tag them, right? So the tag would be the rest of the bits in this example that are going to be used to identify if I have the correct data that I'm looking for. So we answered the question of where to put it. We also answered the question of where to look at and how to identify if I have the data I want in the cache. Now, the last question that I asked in the previous slide was, if I don't have a space, what should I do? Which memory should I evict? So let's go back to this example. Let me tidy it up. Let's assume that currently I have cached this blue byte. So the tag is basically 01, which is the tag for this guy. Now, what happens if I want to bring this data? This red cell. Now I'm going to go to the cache. I'm going to compare the tag with the tag, and I'm going to recognize that these two are not equal. So whatever I have in the cache is not this data. Now, in this particular example, I don't have any other option. So this byte has to come in this particular byte of cache. So there is no flexibility. If you remember, DirectMap Cache was the least flexible design because I only have one choice for caching. Well, if I don't have any other choice, then, well, I don't. So I'm going to evict the one that I have already cached and then put the new data. So I'm going to evict the blue one. I'm going to put the red one, and I'm going to change the tag to 01. Now, if I had a two-way set associative, if I have a set with two blocks, then at that point I have two options to cache this newcomer. I can cache it in the first block of my set or in the second block of my set. So then I can make a decision which one I choose. If I have four-way set associative, then I have four options. I can choose between the four different options. And we'll talk about different cache eviction policies. So in DirectMap Cache, we don't have any other option. There is only one place I can cache my data. So if that place is full, then I'm going to evict that place. With higher set associativity, with higher number of ways, then I might have different options. So with 2, I have 2 options. With 4, I have 4 options. With 8, I have 8 options. Then I have to have an algorithm that gives me which one of the blocks in this set I should evict to bring a new block. So this is probably a good point to answer questions. If a set holds m number of blocks, then would the search time be OM? Yes. The search time would be OM. Basically, you have to search m different caches. The way it's implemented in hardware is not going to be sequential. You're not going to sequentially go through all the options. So let's say if your set has m blocks, in order for you to check the tags, one option is to start with the first block and set the check the tag, and then go to the second one and then the third one. And in that case, it would be OM. So you have to check m different blocks. But the implementation in hardware is that you can do that simultaneously. You can, in parallel, check the tag for all the blocks in your set to see if you have cached the data. So in that case, OM doesn't make sense in terms of time. It makes sense in terms of hardware circuit, because then you have to have different circuitry for checking m different blocks at the same time. So that's why you have to have more hardware, and that's why it becomes slower. So that was a good question. So there is OM, but it's not necessarily time. It's usually it means more hardware needed, and more hardware means more time in terms of searching, but not particularly, OM. Okay, so do we need to account for the size of the tags when calculating the size of a cache? It seems like adding a tag for each cache location seems wasteful, since each cache location only stores 1 byte. That's a good point. That's why we don't have caches that with block size of 1. So usually you have larger block sizes so that the number of bits that you need for tag decreases. So that's a good observation. So usually block sizes are 32, 128. So the block size is bigger than just 1 byte, so that we're left with less number of bits for our tag. I'll talk about that later. So that both of the two questions were good questions. Okay, so let's continue. Now let's run the same example with fully associative cache. Now with fully associative cache, all the cache bytes belong to the same set. So everything is one set. So all of them are set 0. Now all the caches are mapped to everywhere, right? So each particular memory block could go anywhere in the cache because all of them belong to the same set. Okay, so this kind of makes the search, it's flexible, but it makes the search harder. So how do you now search? Now, in order for you to search, you need all the bits of address as tag. So where is your data, right? You have to look at all these cache locations to see if you have your data. For that, you need a tag. And unfortunately, in this case, you have to use all the bits of your address as tag because nothing else would identify if you have the block that you need in a certain location. So you tag your caches with the entire address. So this gives us the highest flexibility. It also gives us the most expensive hardware, right? Starting from this tag, I need a lot of tag. And now the other question is, how do I search these tags, right? So I will need a lot of circuit to just search these tags in parallel to find the tag for the particular address that I'm looking for. Okay, so to just put all of this together, going back to the example that we had, so again, a memory with 32 bytes and a cache with 8 bytes. So with DirectMap, each particular location can go to a particular set, basically by looking at the last 3 bits, which is kind of equal to just getting a mode by 8, right? So given the address, mode 8 gives you the set. With two-way set associative cache, each set has 2 bytes. So I have 8 bytes divided by 2. I will have 4 sets. So this is set 0, byte 1 and byte 2. This is set 1, byte first byte, and then set 1, second byte. This is set 2, first byte, set 2, third byte, and then set 3, first byte, and set 3, second byte. Now, I can now get the mode of over 4 because I have 4 sets. I don't have 8 sets. That gives me the set number. Now I have to search between the 2 blocks. So I will need a tag. So in the first one, I need 2 bits of tag. In the second one, I need 3 bits of tag, right? Because I'm using 2 bits for set. The rest of the bits I'm going to be using for the tag. And with fully associative, I'm not there is only one set, so no bit is going to be used for set. So no bit is going to be used for set. All the bits are going to be used for tag. Okay, so I have another question here. For bigger block size, would they be stored in address aligned chunks, e.g. storing data in address with 8-byte blocks would mean a block starting? Yes, we have alignment. Of course, yeah. Starting from 0, the next 8 bytes are going to be in block 1, and then the next 8 bytes are going to be block 2, and so on and so forth. Yes, so consecutive bytes will constitute a single block, aligned from 0, starting from 0. Okay. So here is a full picture. It's kind of like close to computer architecture course, so I'm not going to spend that much time on it. Now, this one assumes that each block has multiple bytes. It's not just one byte. So in the previous example that we saw right here in the previous slide, right, each block is 1 byte. So I don't need to look at different bytes in a block. So I don't need any bits to go for block. But if a block is larger than a single byte, then this is kind of like the index in the page table stuff that we saw, right? If my page is 4 kilobyte, I need 10 bits for each byte. Now, if my block is 32 bytes, then I need 5 bits to see which byte of the block I need, right? So this is the size. This is log block size. So if block size is 32, this means 5 bits. Okay, so that's the first one, byte select. Then, depending on the number of sets, I need cache index. So if I have 4 sets, then I need 2 bits to find the cache set. If I have, I don't know, 128 sets, then I need 7 bits. So you know that, right? That as many sets I have, log of a number of sets would be the number of bits that I need for indexing, and the rest of it I'm going to use for cache, for tag. Hopefully this is at this point clear. Okay, now let's look at DirectMap Cache implementation. So with DirectMap Cache, let's assume that what are the, so yeah, so let's look at a particular example. Let's say that my cache is 1 kilobyte, and let's assume that each block is 32 bytes. So I need 4 bytes for sorry, 5 bits for my byte select within each block, right? Now, if I look at a because I have a direct map, right? So how many sets do I have? So the size of my cache is 1 kilobyte, so that's 2 to 10 bytes. Each block is 2 to 5 bytes. So how many blocks do I have? The number of blocks I have is 2 to 5 blocks. And this is basically the number of sets, 2 to 5 sets, because each block belongs to a set, because I have direct map. So each set has only 1 block. So I have 2 to 5 sets. Therefore, I need 5 bits for set number, and the rest of it is going to be cache tag. So here is an example. I'm going to look at the cache index to find the set I need, right? And then I'm going to search the tag to find out if I have the data I need, right? So this is my block. Then I look at the byte select to find the particular byte within that block, and I have to also check the tag to see if the tag is equal to the address. That gives me the answer if I can find my block in the cache. Now with set associativity, things are going to be a little bit different, right? Because now going back to the same example, the number of bytes is not going to change because I still have the size of my blocks haven't changed. Let's say it's still 32 bits. Sorry, 32 bytes. That means that I need 5 bits for my byte select. Now let's say that I have two-way set associative cache. Now previously we saw that in the cache I have 2 to 5 blocks. Now if I have two-way set associativity, then 2 blocks per set, that gives me 2 to 4 sets. So now the number of sets I have reduced, obviously, right? With DirectMap Cache, all the blocks belong to the same set. With two-way set associativity, every 2 blocks belong to one set. So I have less sets. So therefore, I need less number of bits. I need 4 bits this time for my cache index, and the rest of the bits are being used for tag. So now here, as you can see, because I have two-way set associative, each set has 2 blocks. So these are the first blocks, and these are the second blocks. So I look at my cache index. So this gives me 2 blocks. Now I have to search for both of these 2 blocks. What do I use? I use the cache tag. So I check the tag for both of them. The one that hits, I'm going to look at also the valid invalid bits, and that will give us a hit or miss. So as you can see, I have more circuit. As I added more set associativity, I added more circuit. First of all, my tags are bigger. Second of all, I have to do all these tests, all these checks that I didn't have previously. Right. Now, fully associative cache, this means that I basically don't need any bits for my set, right? Because there is only one set, so I don't need any bits. Here are the 5 bits that I used for my block size. The rest of them are going to be used as tag, so I'm going to have a really huge tag. Now, my data could be anywhere in cache, so I have to check all these tags. So I will choose the byte that I need. So it could be like this one is a 00000, for example. If it was 00001, then I would look at these bytes, and so on and so forth. So you pick the byte. Now the next is to check the tag. So now you have to check all the tags because your data could be anywhere in the cache. And then you get your heat ratio, right? Sorry, you get your heat signal. If you hit in the cache, that means that you have found your tag somewhere in the cache. Okay. So the other thing that we have to look at is how caches are used in conjunction with virtual memory, because cache usually uses physical address. It doesn't use the virtual address. Now, if the physical pages that are assigned to a process, all of them are mapped to the same set. So the process is generating virtual addresses that are contiguous, right? They're sequential. So they're all over the place, the virtual addresses. But then I have this mapping between virtual addresses to physical addresses. Now, it could well be that the physical pages that I give to this particular process, all of them are aligned. It could be, right? The addresses of these pages by chance might get aligned, and all of them might be, mapped to the same set. For example, if I go back, to this figure, right, I could potentially allocate this byte. I could allocate this byte, this byte, this byte, and this byte to the process, right? The process is generating sequential virtual addresses, but then the mapping could be mapped to these physical pages or physical bytes. I mean, when you talk about pages, you're going to talk about more than one byte, but you get the idea. They could be aligned, and they could all be mapped to the same set. So in that case, no matter how big your cache is, the application cannot use it because all of its pages are mapped to the same set, or a limited number of sets. So this would be a problem, right? Because we're basically wasting cache. A cache, like all these other bytes, are not being used because all the memory, physical memory addresses are mapped to these two sets, for example, just as an example. Now, how do you prevent this? In order to prevent this, there is a nice algorithm called page coloring. So the idea is to color your physical pages, color your cache as well, and make sure. So basically, first you start with coloring your caches, right? So each cache set gets a color. Each color here represents a different set, for example. I'm just giving you the high level. Now you go and color your physical memory based on where they map to the cache. So all the pages that cache to this red set, you color them red. All the pages that are mapped to this set, you color them orange, brown, yellow, and so on and so forth. So this way you get your physical memory colored. Now, when it comes to allocating or mapping virtual memory to physical memory, all you need to do is to make sure that different virtual addresses get different colors. So as long as you don't allocate the same color, you don't map. So don't forget, the operating system is going to map virtual page number to physical page number, right? So for physical pages, I have colors. So as long as I make sure that different ranges of virtual page number get different colors, so these two have different colors, these two have different colors, so on and so forth. So as long as I use all the colors that I have in my mapping, then I make sure that my application can use all the cache sets. So I'm not mapping everything that my application needs to the same cache. So that's the high-level idea behind page coloring. Okay. Now, let's talk about cache misses. What are the reasons that you might miss in your cache? The first one is compulsory cache misses. So these are the misses that happen when you first start addressing certain memory location, right? So you haven't been accessing this. This is a new page that you need. So there's no reason to expect to find this in your cache because this is the first time you need it, right? So this is compulsory. This is a cold access. For these, there's not much we can do, right? So, you know, unless you can predict in future that you're going to need this address, there's no way for you to cache it. Oh, I got a question here. Is page coloring only applicable to L1 caches? How do we handle L2 and L3, which might have a different cache structure? That's a very good question. In fact, I actually don't know the answer, but I don't think that page coloring is applicable to L1. If I'm not mistaken, if I'm not mistaken, I mean, I really don't know. So this is a really good question. So my guess is you will have to do page coloring for last level cache because that's where you have the maximum number of sets because then the size of the cache is bigger, assuming that all your caches are the same number of ways. So if you have, you know, set associativity that is, let's say 2 or 3, let's assume that all your caches are 2 or 3 way set associative, then the maximum number of sets that you have is going to happen in your last level cache. So that's where you have the maximum number of colors that you're going to use. Now, if you make sure that you're using all those colors for last level cache, then I would expect to see all those colors happening in first level cache as well. But if you do it vice versa, if you do use just colors for first level cache, then in your last level cache, you're going to be seeing the same colors being used. So again, this is a good question. I actually don't know the answer. I have to look it up. But if I were to guess, is that they do it for last level cache. I got another question. How do we determine the number of colors to use for page coloring? Well, that's the number of sets you have, right? So for what am I going? For each set, you use a different color, right? In the best case scenario, for each set, in best case scenario, for each set, you use a different color. If that's too much, if you have too many different sets, you can just, you know, pick a, you know, a smaller number. Obviously, the more colors you have, the better your allocation becomes, the better cache usage becomes. Of course, it also increases your the complexity of your algorithm, right? The maximum number of cache, the maximum number of colors that you need is basically the maximum number of sets that you have. So obviously, if your cache is fully set associative, then you don't need page coloring at all, because your pages could be anywhere in the cache, so you don't have any problem. But with direct cache is the most restrictive case, where you have as many sets as the number of blocks in your cache. Okay, we're talking about the nature of cache misses. We talked about compulsory cache misses. The second one is capacity. So these are the cache misses that you basically don't have more space, right? So if your cache is small, then you will have a lot of capacity misses. The way to solve it is to basically make your cache bigger, right? That's you can deal with capacity caches. Then the next kind of cache miss type is conflict caches or collision misses. So these are the ones that you map the same different addresses to the same set, right? So within your set, you have only a limited number of blocks that you have, and this is conflict. Now, two ways to resolve this: make your cache bigger so that you have less number of blocks per set, because you have more sets, then each set is mapped to less number of memory blocks. So that's first option. The second option is to increase your set associativity, have more blocks per set. So these are the two options you have. The last one in this slide set is the coherence cache misses. So because I didn't talk about cache coherence in SE350, so I'm going to just very high level tell you that in a multiprocessor where you have multiple caches, you need to make these caches be coherent. So the data, if cache of core 1 contains the data for a particular address, then other caches for other cores should have the same data if they want to read. So you shouldn't have a case where data is updated in one cache and in another cache you have an outdated data for the same address. Now, in order to implement this, multiprocessors implement cache coherence protocols, and cache coherence protocols have sometimes really complicated structure and algorithm, and they might evict a cache because somebody else needs it, right? So let's say you have been having read access to a cache, and now somebody wants to write to this cache. The cache coherence could invalidate your cache because it wants you not to have an outdated version. Now, you have, if next time you access your cache, you're going to get a miss because the data got invalidated by the cache coherence protocol. So this is like a coherence miss. Which we're not going to talk about much. So just so that you know this exists, I have included in the slide. But since we didn't talk about cache coherency, we're going to just leave it as that. Okay, so I got a question. Where is the color of each page stored? So this is a good question. So page coloring is implemented by the operating system. So it's not something that that is done by hardware. So operating system is in charge, because operating system is the one that does the mapping between virtual page number and physical page number. So, operating system could decide and the color is basically some notion of just a number, right? We don't really care about red, blue stuff. We care about these numbers. We can associate each color with a number. Now I can look at the address of my page and do mode whatever the number of sets I have to see what color this page has, this physical page, right? So it's kind of like processing the address of the physical page to see what color it has, just to identify where it gets mapped in the cache. And operating system can do that by just knowing the address of the page. Okay. Now let's talk about replacement policy. If you have options, so in DirectMap Cache, you don't have any option. Each cache block is one set. So there's no multiple options to evict. You have to evict the same cache block in the set. Now, if you have a two-way associative cache, then you have two options for eviction. So let's say both of them are used, both of them have different tags, and both of them are valid. And now you want to cache a new data in this set. So you have an option to evict. Now, how do you evict? Well, you could randomly evict. You could randomly pick which block you want to evict. That's fine. This introduces a lot of but you could introduce a lot of randomness and fluctuation in the execution of your programs, and it doesn't necessarily give you a good performance. Let's say one of these 2 bytes, I'm using it a lot, and the other byte, although it's valid, I'm not using it anymore, right? So maybe it's a better idea to evict the block that I'm not using. Now, there are different algorithms for that. So, for example, you can evict the cache block that you used least recently, right? So if there is a cache block that you recently used, you keep it and you evict the one that you used furthest in the past. I'll talk about this when we talk about paging, because with paging we're going to do the same stuff, right? So in this slide, I'm basically talking about let's say L1 or L2 or L3 as a cache for memory. Now later on, when we talk about paging, we're going to talk about memory as a cache for your storage. So all the same topics that we talked about will come up. So again, when we're using memory as a cache for storage, we will get into a situation where we want to evict a page and bring another page from the storage. So we have to evict one page. Now, which page we choose to evict, we're going to introduce some algorithms to pick the page to be evicted. So for this, wait a little bit until we start talking about paging. Okay, how does caching work with multiple processes sharing a cache? That's a good question. So old systems, like let's say 10 years ago, cache would be just shared. Whoever uses it more gets more benefit out of it, right? So cache wouldn't necessarily care about which process is using it, because as I discussed, the cache uses physical address and each physical page is mapped to one process. So who cares? I'm just caching physical pages. That led to a lot of unfair allocations of cache between processes. So if you had one process that was very aggressive, was using a lot of cache blocks, then they would just, starve everybody else. Now, new hardware, so Intel, AMD, they all have some notion of cache partitioning. So you can partition your cache between different processes. You can say, I'm going to use certain sets, for example, for certain processes, and so on and so forth. So you could potentially partition your cache between different processes and limit their access to the cache. So that's a topic for advanced computer architecture probably. Okay. Now, when we write to cache, there are two options. One is write through, one is write back. So with write through, if you are writing, you write both in the cache and you also write in memory. So it happens in both the cache and memory, right? Now, with this one, if you have a read miss, so if you want to read and it misses, then it doesn't require a write. Now you can compare that with this one. So you might actually at this point say, what does this even mean? So wait for that. Now the downside is that writing to memory is slower than writing to cache. So this one, you have to hold on to your write until you get an acknowledgement that the write has been applied to memory as well. So you're slowing down all your writes because you're requiring them to also be written in memory, right? So it's a slower. The alternative is write back. So with write back, you only write to cache, and then you set a dirty bit in cache saying that this cache block has been written to. Now, you don't need to do anything until when you want to evict this cache block. Maybe your memory, your cache is full and you need more space, and now you want to evict. At the time of eviction, then you write to memory. So this allows you to, speed up your writes, because your writes are going to just hit in the cache. And if you have multiple writes, they all can just go to cache. And then at the end, you write the last update to memory. Whereas with write through, you're going to update your memory continuously with all the writes. With write back, all the writes could happen in the cache, and then eventually the last one goes to memory. Now, this one gives us good performance, right? It prevents repeated writes to DRAM. We don't need to hold up on our writes, so it's faster as well. It's more complex, so you have to add this dirty bit, and then you have to also, have some mechanism to, if you end up evicting a dirty block, you have to go and write it back to the memory. So it needs more. It's more complex. Now, this is where we go back and circle back to the first green bullet in this slide. Now, if in this one, in write back, if you read, a read could initiate an eviction, right? So this is your cache. Bunch of, and then let's say this is dirty bit, and there are a bunch of blocks that are set as dirty bit. Now you issue a read. Let's say your cache doesn't, it's a miss. So if it is a miss, then you're going to go to memory to read from memory. And on the way back, you're going to update your cache, right? Now that you have the data, you want to cache it. So this requires an eviction. Now, this eviction you could evict a non-dirty block, but you could also evict one of these dirty ones, right? If this is evicted, then before you can actually evict it, you have to write the data back. So what happened was your read request ended up producing a write to memory because of the eviction. So a read miss could require a write back. Now, this did not exist with write through, right? Because with write through, you don't need to write anything because it's already written to memory. So a read miss doesn't result in a write. But with write back, it's not the case. So a read could result in a write. Okay, now here is a segue from all the discussions that we had about caching to the address translation that we discussed. Now, in the last, not the last one, but in the page table, multi-level page table address translation, we came across this x86 model with 4 levels of page tables. Now, for every single translation, I need to access memory 4 times. Let's see, 1, 2, 3, 4, 4 times to get the translation, right? For the physical block, and then eventually I'm going to access that physical page and read the bytes that I needed. So 4 memory accesses for each memory access. So my program said load this address to, I don't know, register A1. So this is one memory access. But then this address was a virtual address, and to translate it to physical address, I need 4 memory accesses. That's super expensive. So for each memory access, I need 4 memory accesses. Now, how many memory access do I need to do per instruction? Remember, I told you for every instruction, we need to go to memory at least once. So now this means that for every instruction, I need to go to memory 5 times. 4 times to translate and 1 time to eventually fetch the instruction I need. So is that really what is happening in today's computers? If that was the case, our computers should be super slow because each memory access is super slow. Now, you probably know the answer because your systems are fast. The answer is that we really don't do this all the time. And how we avoid doing this is by caching the translations. So if I end up actually going through these 4 levels to do a translation, now that I have the translation, now that I know virtual page number 5 is mapped to physical page number 10, now that I have this translation, it's wasteful to throw it away because we already saw that our memory accesses have temporal and a spatial what is it? Temporal and a spatial. Yeah, I'm definitely getting old, or maybe my brain has issue. Locality, right? We have temporal and spatial locality. So there is a high chance that I'm going to need this same translation next time, right? For one, if my page is like, I don't know, 4 kilobyte, probably all the data that I need probably is in the same page. So for all of them, I need a single translation from the virtual page to physical page. So if I do this single translation, I can use this for all the memory accesses. Let's assume that all the data that I need fits in a single page. Then I do the translation once, and then I use it. I don't need to do it again and again and again. So page table resides in main memory. So every time you want to translate your address, you're going to go to main memory, and that's expensive. So we can cache the translations very close to the CPU. So that's where we put TLBs. So this address translation is going to go to TLB, translation look ahead buffers. So the main idea is to cache these translations and put them in this sense is this data structure, this register file, or whatever you want to name it in hardware, to store all these already translated memory accesses, and then use them. Now, as I said, the reason this is going to work is because we know we have a spatial and temporal locality. So here is what we're going to do. So we're going to put this TLB. This is the cache for address translation. So this is going to be close to CPU. Now, page table resides indeed in physical memory, so don't be fooled by this picture. So page table is indeed in physical memory. So this is in memory. I'm just separating it from it to separate address translation and data access. But in a sense, both of them are in memory. So the CPU is going to generate virtual address. I'm going to look at the TLB first to see if this virtual page number has been already translated to a physical page number. If I find the translation, if I hit in TLB, now I have the address. So I can use the translated address that was cached to go to physical memory and get the data I want. If I miss in TLB, then I have to go through my page table. So this miss is an expensive miss. So if I miss, then this means maybe four page walks. And then, if you get a miss and you go and translate your address, then you can cache that address in your TLB. And if if there is an address that is invalid in your page table, then you get to raise an exception. Okay, so now let's look at some of the issues that TLB could introduce. If I reduce the permission of a page in page table, so operating system always works with this page table. Let's say that this page I had given read and write permission to this process. Now I want to change the permission to just read only. So operating system goes and changes the permission in page table to say, now this is read only. Now, if the address is translated in TLB, what should happen, right, in the TLB? Because I'm not going to go to page table all the time. First, I'm going to go to TLB, and if I find this in TLB, I'm going to use it in TLB. So, if you reduce permission, then you have to make sure that the TLB is no longer caching that translation. So in older computers, you have to flush the entire TLB because in older generations of architectures, we didn't have any way to discard a single page table entry in TLB. So we had to flush the entire TLB. But in new machines, in new architectures, we can indeed invalidate a single entry in TLB. So if that's the case, we have to invalidate that single entry in TLB. Otherwise, we have to flush the entire TLB. If permission is added, do I need to do anything? So if instead of, let's say this page had a read-only access, now operating system has made it read and write. Do I need to do anything? In this case, no, you don't need to do anything, because what's going to happen is if the process attempts to write, you're going to go to TLB. TLB is going to say, oh, it's read only. So it's going to raise an exception. Then operating system wakes up and operating system says, oh, it's OK. So this is OK. And then the hardware can update the TLB. So you don't need to do anything. If you invalidate a page table entry, let's say you swap a page to memory and you invalidate the address translation, you have to do the same thing that we did in the first bullet. So you have to invalidate the page table entry in your TLB as well. So you have to tell the TLB that this translation is no longer valid. So you can't just focus on page table. You have to also do it in TLB. Okay. Now, a little bit of kind of like playing with this dirty bit and access bit in TLB. So we talked about page table entry having an access bit and a dirty bit, right? Now, access bit, we don't, usually TLBs don't cache the access bit of a page table entry, right? So if you're caching a page table entry in your TLB, this means that you have already accessed it. So the hardware has set the access bit in the page table, right? So again, so you have this TLB, which is a cache for your page table. So if you have a single PTE here, page table entry, that you cached from here, page table entry. So if you have cached this guy here, the hardware has already set the access bit. So there is no point in caching that access bit here, right? So you don't do it. This usually you don't have it. So every time you cache, you set the access bit in page table. You don't have it in TLB. What about dirty bit? Now, dirty bit is different because initially when you cached the page table entry in your TLB, it might have been just for a read. So you might have had a read request, and then you cached the translation in your TLB. Now, maybe next access is a write. So you cannot expect the hardware to have set the dirty bit in page table entry because maybe the first one was just a read. So as a result, you need to have a dirty bit in your TLB, right? So you have to have this dirty bit in your TLB. So when you write, you can then set the dirty bit in TLB. And also in PT, it's kind of like a write back. So you set this dirty bit in your TLB. You also then go and set it in your PTE. The reason you do a write back here is because in the future, if you go and write, you don't need to then go to PTE, because if this write back is set here, if this is 1, if the dirty bit is set to 1, this means that I've already write back a 1 in my page table, so I don't need to go to page table anymore. So if you continuously are writing to a page, you just do a write back to page table, setting the dirty bit, and the rest of them, because you have cached this dirty bit in your TLB, you know that you don't need to go and change the dirty bit in your page table. Now, do we really need this dirty bit in page table entry and TLB? The answer is no, we really don't need it, right? So initially we had this dirty bit because we wanted to, know if in the case where you want to evict a page, do you need to go and write it, write the changes in the disk? So you can make everybody all the pages read only. This is how you can emulate. Let's say if you didn't have a dirty bit, right? Then every time you have a write, then the hardware is going to check the page table and see that this was a read only address. So then the hardware is going to wake operating system up and say, oh, I'm going to write to this page, so you need to know. Then operating system will know about this write. right? Because the entire purpose of having this dirty bit is to tell operating system that this page has been written to, right? Whenever the operating system checks this page table entry, if the dirty bit is set to 1, this means that the hardware is telling me that there has been an update to this page. Now, for the hardware to tell me, I don't need this dirty bit. I can just set this page to read only, and then every time the application attempts to write to this page, the hardware is going to wake me up because this is an access that is not granted. So then I'll wake up, and then I can internally in software set a bit to know that this page has been updated, right? The same with access bit, right? You don't need this access bit for hardware to tell you that this page table entry was accessed. All you need to do is to make everything invalid. Then the first access will wake the operating system up, and then operating system can set this access bit internally in software so that it knows that this page was used, right? So you don't need these 2 bits. You can emulate them, but this emulation has a cost, right? It requires the operating system to be invoked. Basically, a page fault has to happen. To avoid this, we put this dirty bit and access bit and allow hardware to set them in the background without waking the operating system up. So this is a now you will see where these are used, right? I'm just telling you now that we need to know a page is accessed, or we need to know a page was written to and updated, but I haven't yet told you why do we need it. So I alluded to it, that we will need it when we are doing paging, but we'll come back to it, right? So so that's that. Okay, I was hoping to finish this, but I couldn't. So I have another 3 minutes. Let's see what we can do. What are homonyms? Homonyms are single virtual addresses that are mapped to different physical addresses. Now you might ask, what is that even possible to have a single virtual address mapped to 2 different physical addresses? The answer is yes. So you could have a single virtual address in process 1 is mapped to a single physical address, but then the same virtual address in process 2 could be mapped to a different physical address. So then I might have a single virtual address in one process mapped to a physical page, and in another process mapped to another physical page. Now, why is this important? Well, in TLB, we're caching virtual to physical address translation. Now, if I don't know which process this virtual address belongs to, I might make a mistake. So I might cache the virtual to physical address translation for process 1, and then I might context switch to process 2. And now process 2 uses the same virtual address, and I think that I have the translation because I hit in TLB, but in reality, this is not a valid translation. This is a translation for process 1. The translation for process 2 differs. So one thing I can do is after every context switch, I can just invalidate all TLB entries. I can just flush my TLB and say, okay, now plain slate, let's cache again. Now, the problem with this is wasteful because I might immediately context switch back to my process for some reason. Maybe this process, the first instruction is mutex.lock, and it's going to be blocked. So if I flush my TLB and then go back to the same process, then I have to cache again. And that's wasteful. So it's simple, but it's expensive in terms of performance cost. Alternative to this is to use a tag. I can use the process ID. So it has actually a different name. It has a process context identification. But what it is basically the PID, a unique ID for each process. I can tag my virtual addresses with this process ID. It's very similar to the tagging that we talked about in caches. So I tag each address with the process ID. Now, if I'm hitting in TLB for a certain virtual page number, I have to check the tag and make sure that the process ID that I'm running right now matches the tag for this TLB. And if so, then I have a hit. If not, then I have a miss. Now, this is in terms of performance, it's better because we're not invalidating all the translations that we have, but it definitely requires more hardware to implement. And adding more hardware means that we're making our TLBs slower, right? Because more hardware means more logic and a slower execution. Okay, I'm going to stop here. How many more slides do I have? Oof. Yeah, I was hoping to finish the. My guess is the rest of them are going to be straightforward, or I'm hoping at least. Okay, so anyhow, thank you for sticking around, and thank you to those of you who are watching online. Actually, offline. You're watching online, but in an offline fashion. Anyhow, so thank you. Take care, be safe. We'll talk to you on Thursday. Bye.